Hey there. Now that we have a good idea about what a composition of functions actually means, we're going to practice that. But at the same time, we're going to explore what the domain of a composite function, or when you compose two functions or composition functions, how you find that, like what that is, because it's really important. Sometimes when we compose functions, they end up losing some pieces that we need to know for the domain. And so I'm going to give you a very good technique on how you deal with the domain of composite functions, which is important to know, especially when we get into exponentials and logarithms and calculus. So let's take a look at an easy example that we have done in the last video, and I'll tell you what all of this stuff means. So let's start learning about it. If I give you two functions f and g, and I ask you to compose them f of g, or any sort of permutation of those two functions, we know that we take the first function, open up with a blank space, and put the second entire function inside of it. So I'm going to call this the inside function, the function you're composing and the function you're composing upon. So this g of x, this inside function, that's really important. We need to understand the domain of that inside function. That is the most important thing that I can get you to know, is find that first and don't lose it. You see, when we find a composition of two functions, or a composite function, we'd say, the domain's a combination of two pieces. It's the domain of the inside function and the domain of the simplified composition that we get. So the whole idea, and it's not hard, you just need to know it. The whole idea is you find the domain of really both functions, because we most of the time compose f of g and g of f at this, both of them almost all the time. And so it's really useful to find your domains first. But in general, you find the domain of the inside function first. So we look at this, we say, that's my inside function. That's my inside function. Find your domain. Do the composition, simplify the composition, find the domain of the simplified composition, and then combine those two. That's all there is to it. So here's what we would do. Here's a process. These domains are going to be all real numbers I talked about in the last video, but here's what we would do. I'm going to find f of g of x, and I know it's already done. So, and I've actually erased some of it there. That doesn't really matter. So I know it's already done. Here's the thought process. Here's my inside function, it's g of x. I know this is going to go inside f of x. So I'm going to look at g of x. I'm going to find my domain. So in my head, I'm thinking, okay, what's the domain? I don't see any square roots. Good news. I don't see any denominators with variables in them. That's good news. I don't see any logarithms. That's good news. That means the domain, in the absence of those three things, is all real numbers. We also can use interval notation, negative infinity to positive infinity. So I know that. That's in the back of my head. The domain of my inside function is right there. Then I do my composition. Okay, I've already done it. I get down to here. This I sort of erased. I think it's 3. And we would take a look at it and say, okay, now that we have a simplified composition of these functions, what's the domain of this? Well, I haven't added any fractions, or I haven't gained any fractions with denominators that have variables in them. I don't have any square roots still, and I don't have any logarithms still. So the domain here is all real numbers. The domain of your composition is a combination of your inside domain and the final domain that you get. So this domain is all real numbers. What we got, domain is still all real numbers. We combine those, you get all real numbers. You don't get double all real numbers, but you get all real numbers. Negative infinity to positive infinity. That is how you find domain. The same thing would happen here. I'm just going to talk through it real quick. The domain of our inside function f is all real numbers. The domain of our final simplified version of our composition is all real numbers. We combine those two, you still have all real numbers. Remember, you're only looking for really 3 things, and one of which we haven't talked about yet. So you're looking for any sort of radicals that have even powers, even fractional powers. So like 1/2 powers, 1/4 powers, or square roots, 4th roots, 6th roots. You're looking for radicals. You're also looking for Fractions that have denominators that could possibly equal 0. So any sort of denominator with a variable, you check that. We're looking for those two things. Do we have them originally? Are we creating them? Those things are important to know. Logarithms come later. We haven't covered them, so you're not going to see them yet. And that's the main idea here. So we're going to move on to some more complicated examples that don't have domains that are all real numbers. But again, this is what we're checking for. All right, let's get after it. We've got an example here where I'd like to find the composition f of g of x and g of f of x with the domains of these things. So keep in mind, we can still do f of f and g of g. I'm just not going to get into it because these are the most common, and if you understand these, you can do those as well. We've already talked about in the last video. So let's find f of g of x. The first thing we want to do before we start this, if we are required to know the domain, which you are almost all of the time, we're going to take the time to find the domain of both of these functions first. Why? So that way we don't forget about it, and that way we don't think that our domain is something that it's not. So I'm going to take a look at this, and I'm going to firstly find the domain of both of these functions. So on f of x, I know that this has a fraction. The denominator has some variables in it, and if we have a denominator that equals 0, we've got a problem. It's going to create a vertical asymptote, but in general, you have something that creates an undefined output. And so we know that x plus 3, if that equals 0, we got some problems. So I know that our domain in simple form here is x cannot equal -3. That would create a problem for us. That's an issue. G of x, I'm going to take the time to find that domain as well. If x equals 0, we have a problem. So the domain of g of x is x cannot equal 0. F of x is x cannot equal -1. All real numbers besides those two values will work just fine in those two functions. Now, we're going to find f of g of x. In your head right now, I want you thinking, what's my inside function? What's the function that I'm not composing into that I'm using to compose onto another function? The inside function here is g of x. You'll see it as we write it, but our inside function is g. What's going to happen? We're going to compose this, we're going to simplify it, and then we're going to take the combination of two different domains. What we get when we're done combined with what was inside when we started. So for sure, our domain is going to have whatever the domain of the inside function is in there somewhere. X cannot equal 0. We know that. It's going to be a combination of the domain of inside and the end. So here's our inside domain. That is why we find it first, because this will not leave us. Now, I warn you, as we get through here, that domain may or may not show up in the final composition. We might simplify it away. It might move from a numerator to a denominator, which is why we find it first. Because if you don't find that first, it's very, very common for students to do this without doing that and then lose that piece because they think, well, oh, you can plug in zeros just fine now. Remember something about domain. You can't ever really make it better. It always carries its baggage with it. So because this came from here, it's always going to have that condition. It's always going to not be able to, it's never going to be able to let you plug in 0, no matter how much it looks like it. So now let's continue with our composition. So this composition says, take a look at the function f. Hey, here's the function f. Replace all of the variables. So if you have a polynomial with many variables, it's every single one of those variables. Replace all of the variables with a parentheses. Now, that's a blank spot for us. So x, hey, blank space. X, blank space. That's what x's mean anyway, this thing that you can plug into. And then plus 3. So we've replaced all of the variables in our first function with blank spaces. Now take your second function in its entirety and plug it in. So I'm going to plug in 2 over x and 2 over x. That is the second function that we're composing into the first function. And now we simplify it. Notice this is where you can identify easily, if you hadn't been able to before, what your inside function is, the function you're composing. So that's going to be 2 over x and 2 over x. And that's where we get our domain from. And then we have to simplify this. And yes, you do have to simplify it. So how do we simplify this? Well, because the parentheses really aren't super relevant right now, just give us a place to put that function. We have 2 over x divided by 2 over x plus 3. This is a complex fraction. how we deal with complex fractions is multiply by the LCD on both the numerator and the denominator. So our LCD here is x. Let's take x, let's multiply it by x over x. Now stop right now and watch what we've done. Please get this. What you've just done, think about it, this will make this make sense. What you've just done is you've multiplied by 1, right? Right? Just follow me here. You've multiplied by 1, but only if x is not 0. Because if x is 0, 0 divided by 0 is not 1. What is it? It's undefined. You can't do this if x is 0. This condition allows you to even do this thing. If this is not here, then you cannot do that if x is 0. That needs to make sense to you. This is not 1 if x is equal to 0. It's undefined if x is equal to 0. It's undefined. You can't do what you're doing if x is allowed to be 0, which is why we have that restriction and why it maintains in this problem, even though it looks like it's going to disappear. You need it. Watch that a couple times if that does not make sense. I've explained it, but it's got to sink in that you wouldn't even be able to do this without that restriction. So we've done it. Now we're going to simplify. Remember that we do distribute. 2 over x times x, your x's are going to cancel. You're going to get 2. Here we distribute 2 over x times x is going to cancel. You're going to get 2. But here nothing cancels. You get plus 3x. So our simplified composition is 2 over 3x plus 2. Notice something. Does it look like you can plug in 0 here? Yeah, no doubt. Like if you were to plug in 0 right now, it'd be just fine if you were allowed to do it. This is why we write down the domain of our inside function and the domain of that inside function first before I did any work. I do this every time. I look at my inside function, I identify my domain, I write it down. Because I know that a lot of times it disappears, so I don't want to lose that. So we've done that, we have it simplified, and now we've also developed another domain problem. Check it out. It's not the same domain problem as this one. It's new, and this happens when we start dividing functions or composing functions. Sometimes we get additional domain restrictions. You've seen that a long time ago. We just get it again in a different context. So we have 2 over 3x plus 2. Oh my gosh, it's a fraction. I've got some variables on the denominator. I know that if my denominator equals 0, I have some problems. So when we subtract 2 and divide by 3, this creates another issue for us, something else that's undefined. So any sort of value that causes this to be undefined is a problem. I'm going to take this, I'm going to also add this to my domain. So I already knew from the inside function x cannot equal 0. We explored that a lot right here, but now I also can't allow x to equal negative 2/3. Any other values besides those are going to be just fine, but those things themselves, those are problems. I hope that makes sense to you. You take your inside domain, you put it down first because it can sometimes disappear and you don't want to lose it. But for the reasons I've already mentioned, you cannot plug in 0, even though it looks like it. We also gain some other domain restrictions. So take the combination of those two ideas, that is your domain. Okay, let's move on to the next one. So g of f of x, well, our inside function changes. We're still going to do the same technique, but before I even start this, I'm going to say, all right, my inside function is f of x. If I can't identify it now, I write g of f of x in this way. I look at g, my first function. I notice that's 2 over x. I'm going to create 2 over a blank space. So that's my first function, g, written in such a way that I can compose into it. I look at my second function, f. Okay, f says x over x plus 3. I'm going to take that x over x plus 3 and I'm going to put it inside this blank space, this variable. This has taken f of x and put it inside the variable of g of x. That's exactly what we want. Now I can really easily identify what my inside function is. My inside function is f of x. It's the second function. So I'm going to start building my domain now. Because I already have this domain, I know that no matter what happens, I'm going to take this domain and I'm going to have that inside the domain of my final composition. So I know for sure that x cannot equal negative 3. I'm going to write it down now so I don't lose it. And I'm probably going to get some other restrictions out of this. Well, we do have a complex fraction again. We know that the LCD is x plus 3, and how we deal with the x plus 3 is we multiply both the numerator and denominator by whatever the LCD is. In this case, x plus 3. Now notice, again, for the same thing here, if you allow x to be negative 3, this doesn't work. If x is negative 3, then this becomes 0 over 0, and that is a problem for us. It's undefined. And so we have to restrict that to let this even work. That's why finding the domain of a composition of functions is so important, because you have to tell it when it's going to work. It is only going to work if you don't allow x to be negative 3. You can't even do this if x is negative 3. So we're going to go ahead and multiply. This is going to distribute, but this is going to cancel. You're multiplying x plus 3 on a numerator and denominator. It's going to cancel, give you 1, but we're left with just x. This right here is the composition g of f of x. So we get 2x plus 6 over x. And then we find the domain again. This one's pretty nice. We look at this and say, hey, if x equals 0, if our denominator equals 0, that's a problem. That would create something that's undefined. So I'm going to combine that with the domain I already have. Notice how it looks like you could plug in negative 3 and be just fine. The only reason we have that is because this came from the inside of our composition, and we can see that we need that to be the case to even simplify this composition. And so we're going to add something else to it. We say, hey, we had that, but we also can't allow 0. But those are the only two restrictions we have. Any other number in the world is going to be just fine in this composition. If you want to see why this is true, why you need this one, try to evaluate. If we try to evaluate negative 3, first we'd run negative 3 through f. And you go, okay, if I evaluate for negative 3, that'd be 0. Wait, oh, right there, we can't do it. Now try to do 0. If we did 0, so evaluate for 0, because this is coming from the end, right? Maybe it doesn't make sense that we couldn't evaluate that, but evaluate for 0. If we put 0 into f first, we get 0 over 3. Now that would be 0. But when I take the output 0 and I put it in here to my first function g, 2 over the output, which was 0, is undefined. So even this one does not work if you try to evaluate it the way that I showed you in the last video, by taking 0, plugging it into f, that's 0, then plugging in that output into g, 2 over 0 is undefined. That's why these are both problems. And that's how we deal with domain. Inside plus end gives you domain of composition. All right, this is the last example that we're going to do. There are some that are a little more complicated, but the idea is what I'm teaching you right now on how to find this. The reason why we're not getting more complicated with the structure of the problems is because that's not what this is about. What this is about is me teaching you how to find the domain. Now, we have dealt with simplifying the algebra of tougher problems. What we haven't done is found the domain yet. That's why we're focused on that. So we're going to compose this f of g of x and g of f of x. We're focused on finding the domain and the aspects that pertain to us. So how we do that is really important. Number one thing we're going to do is we're going to find the domain of both of these functions. Why both? Because we're composing them in two different ways. If we just had this one, I would only be focused on finding the domain of g of x. I wouldn't even care about f, because I take the domain of my second function, my inside function, and whatever I get at the end. F really doesn't play into it in terms of finding the domain first. Here it does, and so that's really important. So composing two different ways affects what domains we want to find. In this case, we're finding both. So I'm going to start with f of x. I'm looking at f of x, I'm thinking, does it have square roots? No. Does it have denominators that have fractions in them? No. Logarithms? No. The domain here is all real numbers. Now we go ahead, we look at g of x, and we say, hey, oh, that's got a square root. That has to have some domain issues if we have x minus 1 inside of it. So we find the domain of g of x and say, oh man, if we think back to it, what is the domain of a square root? What we know is that the inside of our square root has to be greater than or equal to 0. We can't allow negatives inside of square roots in the real number system. That is the way that you don't allow negatives. What you don't do, you don't set this thing equal to 0. It's not a denominator. Don't do that. That shows me that you don't understand the concept. If you're doing that, the concept here is inside, not negative. That's what that means. When we solve this, we get our domain. We know that x has to be greater than or equal to 1 in order to create non-negative numbers, that's 0 and positive, inside of that square root. And so we found our domain. Here's what's going to happen. When we take care of f of g of x, because g of x is our inside function in this composition, our domain is going to have that. No matter what happens, it's going to have that. So I'm going to go do a couple things. I'm going to show the composition. I'm going to identify that g is actually the inside function. I'm going to write the domain, and then we're going to simplify. So our composition says the first thing I want to do is I want to look at the first function f. I want to replace the variables inside of it with some blank spaces. So f is x squared plus 1. I'm going to replace the variables with blank spaces. However many variables there are, you replace them with blank spaces so we can get some complicated things. Now I take a look at my second function. I say, all right, my second function is g of x. That's going to go inside the blank space. So f is x squared plus 1. G is square root of x minus 1. I'm going to stop right now. And if I haven't done it already, I'm going to write out the domain right now, the pieces I understand. My inside function is g of x. I should know it here, but I can really see it here. I'm going to take the domain of this, which I've already found. And then I'm going to simplify it. And if I have to, I'll add additional restrictions in there. So let's go ahead. Wait a minute. Square root squared. We know that every time a power matches a radical, we simplify that. But x minus 1 plus 1 is just x. So f of g of x gave me x. Well, that's interesting. I'm going to tell you something right now that we're going to explore when we get to inverses in a few videos. If you compose two functions and you end up getting x, the two functions you composed are inverses. They're going to undo each other if you compose them. And I can prove it to you right now. If you take any number that you want that's in this domain, and that's a key feature, right? It's got to be in the domain for these to be inverses. We'll talk about that in a minute. But if you take any number, like let's say 10. If I take 10, I plug it into here, take the output, plug it into here, I'm going to get 10 back. That's what inverses do. They undo everything about one another. So just work with me here. If I take 10, 10 minus 1 is 9. The number 9, the square root of 9 is 3. So that's the output, right? I plugged in 10, I got out 3. Take 3, the output, plug it in here now. 3 squared is 9, 9 plus 1 is 10. Wait a minute. I plugged in 10, I got the output, took the output, plug in here, and it gave me back 10. It undid all the math. I plugged in 10, I ran it through both functions, I got out 10. That's what inverses do. They undo each other. That's exactly what this is saying. It says, what are you plugging in? X. What are you getting out? X. Nothing's happening, right? Because they undid each other. Look at the math. This undid this undid this. You have X remaining. Inverses undo one another, and that is why when you compose two inverses, you will always get X. You're plugging in this, you're getting out the same thing. It's undone all the math around it, and that will happen every time with inverses. Now, I said something very specific. I said these are inverses, and that's true, but only on a certain section of the domain, of the x-axis, because it doesn't exist other places. And so these are inverses under your domain that you already identified. And that's pretty neat. You've already seen where these two things are inverses. So as long as x is greater than or equal to 1, this function and that function are inverses because it matches up with our domain. Now, well, let's look back here. Let's finish this up. Does f of g of x have any other domain issues? Well, that doesn't have any square roots, or radicals in general, that are even. This does not have any fractions and variables in the denominator, no logarithms, so this domain is all real numbers, but it does not trump the fact that you have a domain issue already. So we say all real numbers as long as x is greater than or equal to 1. This is there no matter what. Why? Because it had some baggage that we saw. The inside function had a domain issue. We have to have that. And if we don't, then we are wrong on the fact that these two are inverses. Because if we don't have that, we say, oh, they're inverses all the time. No, they're not. No, they're not. They're only inverses on that domain. That's why we need it. All right, let's talk about the last one. If you've done it already, awesome. If not, you can pause the video and see at least if you can do the composition. So g of f of x says, let's take a look at our first function. The first function is g, so I'm going to replace my variables with some sort of blank space, something I can plug into and evaluate that holds everything together. That's what parentheses do for us. Then I take a look at my second function, f of x. I go, okay, f of x is x squared plus 1. I put the entire function in all the parentheses I've created. There's only one in this case. And before I simplify, I'm going to go ahead and I'm going to start writing out my domain. The domain's a combination. It's a combination of the first function, the inside function, and the final composition after you simplify. So the inside function is f of x from here, and we can see x squared plus 1, and we know that that domain, because we wrote it down already, is all real numbers. So I'm going to write that down. And if I have any domain restrictions, I'll write that along with it. I'll say all real numbers except x can't equal whatever, or all real numbers as long as they're greater than 1. But let's see what happens. Okay, so I have square root of x squared plus 1 minus 1. Well, these 1's are going to give me x squared minus 1, or plus 1 minus 1 is 0. Square root of x squared gives me x. Well, that's interesting. I get the same thing as here. And that is exactly true. If you compose two inverses, no matter which way you compose them, you have to get the same thing. And that same thing will always be x. We talked about y here. We said with inverses, inverses undo each other. They undo everything about themselves so that what you plug in is what you get out in an inverse. Well, if I undo them in the opposite way, what you plug in is still what you get out in an inverse. It's just done differently. And you can see that here. Plus 1, minus 1. Those are inverses. Square root, power 2. Those are also inverses in certain domains. So g of f of x is still equal to x. Now what's interesting is this does not gain me any additional domain issues. So my domain, there's no modification to that. The domain of the inside, all real numbers. The domain of the final composition, all real numbers. Our domain here is all real numbers. Now why are they different? Why is that domain restricted and this domain is not restricted? Why is that? The answer is because when we take a look at what f of x does, take a look at this. Take any number and plug it in. You're going to get 1 or more. Take a look at it. Plug in anything, you're going to get 1 or more. That's your output, right? That's the range of this. So the range of this is 1 or more. The range of your inside function is the input of your the compose upon function. So this has to give you 1 or more. This works as long as your numbers that you're plugging in are 1 or more. Since the outputs here are 1 or more, it matches perfectly with our domain. There's never an issue, which is why we don't have a domain restriction. It's impossible to get something that would give you a negative inside of there with that particular function. I hope that makes sense to you. I hope you're seeing the value in finding domain, that we're not even allowed to really work with these functions unless we meet our domain, which is why we need to know it. So that's how we compose functions. I hope it made it make sense. I hope you understand the blank space and plugging in, and now finding domain. Take the inside, take the final, put them together. Sometimes we don't have issues even when you might expect them. Sometimes we do when you don't expect them. So I'll see you for another video. We're going to start talking about one-to-one functions next, and then inverses, and eventually we'll be mashing all these ideas together. Composition with inverses and one-to-one functions, exponentials and logarithms, and getting something pretty fantastic on how we solve exponential and logarithmic functions. I'll see you for that.